Welcome back everyone to part 3 of our TF Regression Code Along project. So we just, in the previous lecture, ended up training our model and fitting to that training set. Now it's time to explore an evaluation on not just our test data, but also being able to predict the price of a new house given its features. Let's get started. Okay, here we are in the notebook where we left off last time. We just finished training for those 400 epochs. What I'm going to do now is explore what my model history looks like now. So recall, we can get a history of those losses by saying model.history.history, and it returns back this dictionary. However, because we passed in the validation data tuple, what I can now do is when I convert this to a data frame, I not just get my loss on my training set, but I also get this other variable called val_loss. And this is my loss on that test set, that validation data. And now I can directly compare the loss on training versus the loss on test or validation in order to see if I'm overfitting to the training data on my model. And the best way to do that is by simply plotting these. So I will say losses is equal to pd.dataframe, and then I can say losses.plot, and I can directly compare the plot behavior of my blue training loss versus my orange validation loss. And this is exactly the kind of signal we want, where there's decrease in both the training loss and the validation loss, and then there is no increase so far in the validation set. And actually what that means is technically we could have continued training. Now you'll notice that towards the tail end, we're actually not improving that much. So after 400 epochs, it looks like we're kind of hovering around this particular loss value, and the decreasing is happening much slower. But because the validation loss is also going down, that's an indicator that we could continue training without overfitting to our training data. If you saw this orange line begin to spike after some of these epochs, so it started to go up and up and up, that means you're overfitting to the training data because now you have a much larger loss on your validation data. And later on in the lectures, we'll see an example of that, which will allow us to then actually implement what's known as early stopping. In this case, this is pretty much the perfect behavior you want to see. You want to see training loss and validation loss go down and then continue down together. So there's no overfitting that we can see occurring here. Okay, so now let's do some evaluation on our test data. So what we can do is a variety of methods on this. We can say from sklearn.metrics import, and we can import things like the mean squared error, the mean absolute error, and we can also even, if we want, get an explained variance score. So what we do here is we grab our predictions by saying model.predict, and we're going to predict on the test set. So we run that, and now recall we have our list of predictions, and what we're going to do is simply compare these to what we know are the correct values. So we can call mean squared error or mean absolute error. We can do both. And what we do is we first pass in y_true. So recall that is y_test. And then we compare that to our predictions. So our total mean squared error here is this value. This is a very large value, which kind of makes sense because we're dealing with the prices of houses. So we're squaring those. So it should be a large value. This is really hard to interpret. So what we can do is either get the root mean squared error by taking the square root of this, either by running np or np square root. This is our square root error, or root mean squared error. Or what we can do is also get mean absolute error. So mean absolute error, it's really easy to interpret because it's essentially just what is your average absolute error across all your predictions. So we can say y_test versus predictions, and it looks like our mean absolute error, so on average we're off by about $100,000. Now is that good or is that bad? Again, we have to take into account the actual data frame itself. So we have to take into account our price column off the original data frame, call describe on it, and see what kind of values we're actually dealing with. So recall that the mean, it looks like it's 5.4 times 10 to the 5. So if we actually grab this and put it in here as a number, it'll report back that the average price of the house is around $540,000. In our case, our mean absolute error is about $100,000. So that's not really that great. We're off by around 20%. So Not great, not horrible either. What we can also do is use an explained variance score to try to get a deeper understanding of our evaluation metrics here. So I can use explained variance score, and if you do Shift Tab here, it'll essentially explain what's actually happening here. So the best possible score is 1.0, and what this does, it tells you how much variance is being explained by your actual model. And you take a look at the online documentation for further examples of how this actually works and how it actually is calculated. But what we can do here is, same as before, pass in our y-test values versus our predictions, and we're getting an explained variance score of somewhere around 0.8. So in this case, 0.79. So that's just merely okay. Again, it really depends on the context. Do we have a previous model that actually performs better than this? We also notice that technically we could still keep training and keep lowering this loss. So maybe it's worth it to try to keep training on the training data, since we technically haven't actually reached overfitting on it quite yet due to our analysis here. What we can also compare is our predictions, and we can plot them out against a perfect fit. So recall that previously what we did a scatter plot of y-test versus our predictions, and we can see the way they fit here. And what I can do is make this a little larger. So I can say PLT fig size is equal to, let's say 12 by 6, in order to fit everything nicely. Now, in a perfect world, this would be a straight line, and we can compare by saying PLT plot, and I'm just going to plot y-test against y-test, and I'll just say this is a red line by saying R, and now this red line represents the best, or basically the perfect prediction line. You'll notice that we're basically being punished here by these outliers. So these really expensive houses, we're actually not good at predicting the price, but we're pretty good at predicting the prices of houses between $0 and $2 million. This is actually not so bad. There's clearly a good fit here between our tests and our predictions, and that's essentially what explained variance score is trying to report back to you in the form of a single number. What may be worth it is to retrain our model just on that bottom 99% of houses. And so if we come up to a situation where our maybe sale price is over $3 million, we'll just say, sorry, our model's not good enough for this, and we'll only refit to that bottom 99%. Again, it really depends on the context and what questions you're trying to answer and what problems you're trying to solve. Okay, so finally, let's show you how you would use your model to predict on a brand new house. So let's take a look at our original data frame. We'll go ahead and just pick the very first house here. So let's say DF, and what we'll do is we're going to drop the price of this house. So say drop the price along axis is equal to 1, and then just grab the very first house here. So what this is, these are only the features of a new house on the market. So let's say a new house is coming onto the market and you want to sell it in October 2014, and you know these various features of the house. You know how many bedrooms it has, you know how many bathrooms it has, etc. You know its condition, whether or not it's waterfront, etc. So we have all these features for a new house coming onto the market. Now the next step is to actually scale this single house data. Recall that our model is trained on scaled versions of the features, which means we can't actually pass in these features raw. Instead, what we need to do is say single house, grab those values. So now it's a NumPy array, but the shape is actually off. Notice there's only one set of braces or brackets there. I need to reshape this to be -1 by 19. And you'll notice now that essentially adds that extra set of brackets there, which is the shape expected. -1 just basically means keep those old dimensions along that axis. So now that I have it in the correct shape, I should be able to say scalar.transform on this, and now I have the scaled versions of everything. And now we'll reset this to be our single house. So now that I have my single house, I'll say model.predict on my single house, run this, and now I have the predicted price that this will sell at. And if I take a look at DF head the very first item there, just show one. The true price it sold at was $221,000, and I'm predicting it will sell at $288,000. So it looks like we are kind of overshooting here. And again, that may be an issue when we're trying to fit to these extreme values. So an interesting next step to actually undertake would be to retrain your model by dropping out maybe the top 1 or 2% of values and see if that can reduce your mean squared error on your data set. But for right now, I would say we're pretty much done with this project. We've been able to do a little bit of feature engineering, do a little bit of exploratory data analysis, create and train a model, and then get back a relatively reasonable model in order to predict the prices of houses. It's not like we're predicting $2 billion on a 200 grand house. Instead, we're relatively in the range of what a house could sell at. And it looks like we're more or less explaining quite a bit of variance, up to 80% of the variance in the pricing. Okay, so that's it for this lecture. Coming up next, we're going to begin to dive deeper into a lot of these topics based on things like batch sizes and early stopping in our model. And we'll do that by taking a look at classification tasks through TensorFlow. I'll see you at the next lecture.